The universe, in its most fundamental and awe-inspiring mystery, exists in a state that should not be possible. Every atom in your body, every star burning in the night sky, every galaxy spiraling through the cosmos, every grain of sand on every beach of every planet that has ever formed around every sun in the observable universe. All of it, every single particle of matter that makes up the physical reality we inhabit, should not exist. Or rather, it should exist in precisely equal measure alongside an identical universe made entirely of antimatter. And the two should have annihilated each other in a catastrophic flash of pure energy approximately 13.8 billion years ago, leaving behind nothing but a cold, empty, featureless void filled only with photons, the ghostly remnants of a creation that destroyed itself before it ever had a chance to produce a single atom, a single molecule, a single star, a single planet, a single living creature capable of asking why any of this happened at all. The fact that you are reading these words, that your eyes exist to read them, that a brain exists behind those eyes to understand them, that a universe exists around that brain to have produced it. All of this is a consequence of one of the deepest and most baffling asymmetries in all of physics, a tiny, almost imperceptible imbalance between matter and antimatter that occurred in the first fractions of a second after the Big Bang. An imbalance so small that for every billion particles of antimatter that existed in the primordial universe, there were 1,000,000,001 particles of matter. That single extra particle, that 1 in a billion excess, is the reason everything exists. It is the reason you exist. And despite decades of brilliant experimental work and theoretical innovation, physicists still do not fully understand why it happened. To appreciate the depth of this mystery, we must begin at the very beginning. Not just the beginning of the universe, but the beginning of our understanding of antimatter itself. The story starts in 1928 in the mind of one of the most quietly revolutionary figures in the history of science, Paul Dirac. Dirac was a British theoretical physicist of extraordinary mathematical genius, a man so precise in his thinking and so economical in his speech that his colleagues at Cambridge joked that the unit of 1 word per hour should be called a Dirac. He was working on a problem that had been troubling physicists for some years: how to reconcile quantum mechanics, the new theory of the very small with special relativity, Einstein's theory of space and time. The two theories seem to be pulling in different directions. And quantum equations describing the electron, the lightest and most familiar of charged particles, did not behave well when relativistic effects were included. When Dirac sat down to write an equation that was fully consistent with both theories, he produced something that worked beautifully, but it came with a disturbing implication. The equation had not one solution but two. and the second solution described a particle identical in every way to the electron except that it carried a positive electric charge instead of a negative one. Dirac's equation seemed to be predicting the existence of something that had never been observed. A mirror image twin of the electron, opposite in charge but otherwise identical in mass and properties. Dirac himself was initially uncomfortable with this conclusion. He considered various ways to make the second solution go away, or to interpret it as something already known, but eventually he was forced to accept the mathematics. In 1931, he predicted the existence of what he called the anti-electron, which would later be renamed the positron. And in 1932, Carl Anderson, working with cloud chamber experiments at Caltech, found it. A particle came through the detector, leaving a track that curved in the wrong direction for an electron in the applied magnetic field. A track that could only be explained by a positively charged particle with the same mass as an electron. Dirac's mathematical intuition had been right, and physics had encountered antimatter for the first time. What followed was the gradual realization that antimatter was not a quirk specific to electrons but a general feature of nature. Every particle of matter has an antimatter counterpart. A particle with the same mass, the same lifetime, the same interactions with the fundamental forces, but with opposite charge and certain other quantum properties flipped. The antiproton was discovered in 1955 at Berkeley. The antineutron came shortly after. As the particle zoo expanded through the mid-20th century, every new particle was found to have an antiparticle partner. When matter and antimatter meet, they annihilate each other completely, converting all of their mass into pure energy in the form of photons, which is precisely what Einstein's famous equation tells us. Mass is a form of energy, and antimatter-matter annihilation is the most efficient energy release process in nature, converting 100% of the rest mass into radiation, far more efficient than nuclear fission or fusion. This annihilation process works in reverse as well. A photon with sufficient energy can spontaneously create a particle-antiparticle pair out of nothing, a process called pair production. Matter and antimatter are thus not truly distinct substances, but two aspects of a single framework, two sides of a quantum ledger that must always remain balanced when particles are created or destroyed. This is where the cosmological crisis enters the picture. If matter and antimatter are created in equal amounts whenever the laws of physics produce new particles, and if the Big Bang was the most violent and energetic event in the history of the universe, then the Big Bang should have produced matter and antimatter in precisely equal quantities. The universe should have been born with a perfect balance, and if that perfect balance had been maintained, every particle of matter would eventually have found its antimatter partner and annihilated, leaving behind a universe consisting entirely of photons and neutrinos, a vast, featureless sea of radiation, with no structure, no chemistry, no stars, no planets, no biology, no observers. The fact that this did not happen, the fact that there is something rather than nothing, the fact that matter survived and antimatter largely did not, means that some process must have violated the symmetry between matter and antimatter at some point in the early universe. Matter must have had some tiny advantage, some slight preference encoded in the laws of physics that allowed it to win the annihilation war and emerge as the dominant form of substance in the cosmos. Identifying what that process was and why it favored matter over antimatter is the central challenge of what physicists call the baryogenesis problem, because baryons, the class of particles that includes protons and neutrons, are the building blocks of ordinary matter. In 1967, the Soviet physicist Andrei Sakharov, who would later become famous as a dissident and human rights advocate, but who was at that time working in secret on Soviet nuclear weapons before his gradual turn toward pacifism, identified three conditions that any successful theory of baryogenesis must satisfy. These conditions, now known as the Sakharov conditions, have become the organizing framework for thinking about this problem and have guided research in the field for more than half a century. The first condition is simply that there must be some process in nature that violates baryon number, the conserved quantity that counts the total number of baryons minus antibaryons in the system. If baryon number is perfectly conserved, then the net number of baryons in the universe can never change from its initial value. And if the universe started with 0 net baryons, as symmetry arguments suggest, it will always have 0 net baryons. To produce an excess of matter over antimatter, some interaction must be capable of creating baryons without simultaneously creating an equal number of antibaryons, or destroying antibaryons without simultaneously destroying an equal number of baryons. The second Sakharov condition is that the relevant processes must violate C-symmetry and CP symmetry. C-symmetry, or charge conjugation symmetry, is the symmetry that says the laws of physics should look the same if you replace every particle with its antiparticle. If C-symmetry were perfect, then any process that created an excess of matter would be accompanied by an equally strong process creating an excess of antimatter in C-symmetric systems, and the net result would still be 0. CP symmetry goes further. It says the laws of physics should look the same if you both replace every particle with its antiparticle, C transformation, and mirror reflect all spatial coordinates, P transformation. If CP symmetry were perfect, then even with C violation, the combined symmetry would prevent any net matter-antimatter asymmetry from developing. The third Sakharov condition is that all of this must happen out of thermal equilibrium. In a system in perfect thermal equilibrium, detailed balance ensures that every process and its reverse occur at exactly the same rate, which means any baryon number violating process would be exactly undone by its reverse, leaving no net baryon asymmetry. The asymmetry can only be frozen in if the processes occur during a period when the universe is rapidly expanding and cooling, a period of departure from equilibrium. The beautiful thing about the Sakharov conditions is that the standard model of particle physics, our best current theory of the fundamental particles and forces, actually satisfies all three of them, at least in principle. The standard model contains mechanisms for baryon number violation through processes called sphalerons, which are non-perturbative configurations of the weak nuclear field that can change baryon number. It contains CP violation, discovered experimentally in the 1960s in the decays of particles called kaons, and subsequently observed in the decays of B mesons and other particles. And it predicts that in the early universe there was a phase transition, the electroweak phase transition, at which the universe departed from thermal equilibrium in the required way. This sounds like the problem might already be solved, but it is emphatically not. The amount of CP violation that exists in the standard model as measured in laboratory experiments is orders of magnitude too small to account for the observed matter-antimatter asymmetry in the universe. The electroweak phase transition in the standard model is not a strong first-order transition but a smooth crossover, which means it does not produce sufficient departure from equilibrium. The standard model, for all its incredible success in describing particle physics at accessible energies, falls drastically short of explaining why we exist. This is one of the most profound and well-established failures of the standard model, and it is a powerful indication that there must be new physics beyond the standard model waiting to be discovered. Physics that involves greater CP violation and possibly stronger phase transitions. The experimental discovery of CP violation is a story worth telling in some detail because it represents one of the most elegant and unexpected findings in 20th century physics. In 1964, James Cronin and Val Fitch, working at Brookhaven National Laboratory, were studying the decays of neutral kaons, particles made of a quark and a strange antiquark, or their CP conjugates. These particles had been thought to be a nearly perfect laboratory for testing CP symmetry because the two neutral kaon states, which physicists call K short and K long, were believed to decay in ways that were precisely related by CP symmetry. K short decays into 2 pions very quickly, while K long decays into 3 pions more slowly. This was expected to be an exact distinction based on CP symmetry. The 2-pion final state has even CP, and the 3-pion final state has odd CP, so the 2 kaon eigenstates should be perfectly sorted into these channels. Cronin and Fitch found that the K-long, supposedly the CP odd state that should only decay to 3 pions, was in fact also decaying to 2 pions at a small but unmistakable rate of about 2 in 1,000. This was CP violation in action. The laws of physics, at least in the weak nuclear interaction governing kaon decay, were not perfectly symmetric between matter and antimatter. The discovery shocked the physics community and earned Cronin and Fitch the 1980 Nobel Prize in Physics. Since then, CP violation has been observed in several other particle systems, most notably in B mesons studied at dedicated factories at SLAC in California and at KEK in Japan, and more recently in D mesons. Each of these observations has confirmed that CP violation is a real feature of nature, and has allowed physicists to measure the parameters of CP violation in the Standard Model with increasing precision. But the measurements have also confirmed that the magnitude of CP violation in the Standard Model is simply not large enough to account for the matter-antimatter asymmetry of the universe, by a factor that is difficult to overstate. The observed baryon asymmetry requires CP violation about 10 orders of magnitude larger than what the Standard Model provides. Something is missing, and finding it is one of the great goals of contemporary particle physics. One of the most exciting and actively pursued candidates for new sources of CP violation involves the neutrino. Neutrinos are ghostly particles that interact only through the weak nuclear force and gravity, passing through ordinary matter almost without interaction. Billions of neutrinos produced in the sun pass through your body every second without leaving any trace. For most of the 20th century, neutrinos were believed to be massless, which would have meant they always traveled at the speed of light and always came in only one chirality, always left-handed, as opposed to right-handed. But in 1998, the Super Kamiokande experiment in Japan made the remarkable discovery that neutrinos oscillate, that they can spontaneously change from one flavor to another as they travel. This process of neutrino oscillation can only happen if neutrinos have mass, and the discovery, which earned Takaaki Kajita and Arthur MacDonald the 2015 Nobel Prize, was the first clear evidence for physics beyond the Standard Model. But the implications go further than just mass. The same mathematical framework that describes neutrino oscillation also allows for CP violation in the neutrino sector, meaning that neutrinos and antineutrinos might oscillate in different ways. If electron neutrinos and electron antineutrinos transform into muon flavor at different rates, that would be CP violation in the neutrino sector. And it might be much larger than the CP violation seen in quarks. The measurement of this leptonic CP violation has become one of the highest priorities in experimental neutrino physics. The NOVA experiment in the United States and the T2K experiment in Japan have both been collecting data on this question, and preliminary results from T2K have suggested a hint of large CP violation in neutrinos, though the statistical significance was not yet sufficient to claim a discovery. The next generation of experiments, particularly the deep underground neutrino experiment in the United States and the hyper-Kamiokande experiment in Japan, are designed specifically to nail down this measurement with high precision. The theoretical connection between leptonic CP violation and the matter-antimatter asymmetry of the universe runs through a mechanism called leptogenesis, proposed in 1986 by Masataka Fukugita and Tsutomu Yanagida. The idea is that in the very early universe before the electroweak phase transition, very heavy cousins of the neutrino called right-handed neutrinos or heavy neutral leptons decayed in a CP-violating way. The seesaw mechanism, which is the most popular theoretical explanation for why ordinary neutrino masses are so small, actually predicts the existence of these very heavy right-handed neutrinos, and their masses might be anywhere from 1 billion to 10 trillion times the mass of the proton. Because they are so heavy, they would have existed only in the first tiny fractions of a second after the Big Bang, when the temperature of the universe was high enough to produce them. Their CP-violating decay would have generated an excess of leptons over antileptons, and this leptonic asymmetry would then have been converted into a baryonic asymmetry through the Sphaleron processes mentioned earlier, which are efficient at converting lepton number into baryon number at the temperatures of the early universe. Leptogenesis is an elegant and economical mechanism. It solves the baryogenesis problem using particles and interactions that are already motivated by the need to explain neutrino masses, without requiring the introduction of entirely new physics specifically for the purpose of generating the baryon asymmetry. The challenge is that the heavy right-handed neutrinos are far too massive to be produced in any foreseeable particle accelerator. So leptogenesis cannot be directly tested at colliders. Evidence for it must come indirectly through measurements of leptonic CP violation in ordinary neutrinos, and through the search for lepton number violation in processes like neutrinoless double beta decay. Neutrinoless double beta decay is a hypothetical nuclear process that would provide the most direct evidence for the Majorana nature of neutrinos, the property that they are their own antiparticles. In ordinary double beta decay, two neutrons in a nucleus simultaneously decay via the weak force, each producing a proton, an electron, and an electron antineutrino. So the final state has 2 electrons and 2 antineutrinos. If neutrinos are Majorana particles, then the antineutrino emitted by one decay vertex can be absorbed as a neutrino by the other decay vertex. Because for a Majorana particle, the distinction between particle and antiparticle is not fundamental. In this case, the 2 antineutrinos would cancel each other out, and the final state would have only 2 electrons and no neutrinos at all. The signature would be a sharp peak in the combined electron energy spectrum at the end point of the decay. since without neutrinos to carry away energy, the two electrons carry all of the energy of the nuclear transition. Experiments searching for this signal have been running for decades, using isotopes like germanium-76, tellurium-130, and xenon-136, and they have achieved extraordinary sensitivity, probing half-lives longer than 10 to the 26th years, a number so vast that it exceeds the age of the universe by 16 orders of magnitude. So far, no signal has been found, but the experiments continue to improve. The next generation of ton-scale experiments, including Nexo and Legend, may reach the sensitivity needed to discover the signal if neutrinos are Majorana particles, with the masses currently allowed by oscillation data. Another major direction in the search for new sources of CP violation comes from precision measurements of particle properties that are predicted to be extremely small or zero in the Standard Model. One of the most important of these is the electric dipole moment of the electron. An electric dipole moment is essentially a measure of how asymmetrically the electric charge is distributed within a particle. If a particle has a tiny excess of negative charge on one side and positive charge on the other, it has an electric dipole moment. In quantum mechanics, the only way for a fundamental spin-half particle like the electron to have an electric dipole moment is for the laws of physics to violate both parity symmetry and time reversal symmetry. And since CPT symmetry, the combination of charge conjugation, parity, and time reversal, is believed to be an exact symmetry of any consistent quantum field theory. A violation of time reversal symmetry implies a violation of CP symmetry. The Standard Model predicts an electron-electric dipole moment that is so tiny it would require an experiment of literally impossible sensitivity to detect, roughly 10 to the minus 38 times the charge of the electron times a centimeter. But many theories that extend the Standard Model to provide more CP violation for baryogenesis predict electron-electric dipole moments many orders of magnitude larger than this, potentially as large as 10 to the minus 27 or even larger in some scenarios, which is within the reach of current and planned experiments. The ACME experiment at Harvard and its successor ACME III have used polar molecules, specifically thorium monoxide, as exquisitely sensitive probes of the electron-electric dipole moment, exploiting the enormous internal electric fields within polar molecules to amplify sensitivity. ACME2 currently holds the world record for sensitivity to the electron-electric dipole moment, having constrained it to be smaller than about 1 times 10 to the minus 29 electron charge centimeters. This result has already ruled out large classes of supersymmetric models and other theories with TeV-scale new physics. Upcoming experiments, including ACME III and other molecular beam experiments, aim to push the sensitivity down further by another order of magnitude or more, potentially either finding a signal or severely constraining the available theoretical space for baryogenesis models. The direct search for new particles that might mediate additional CP-violating interactions has been the primary mission of the Large Hadron Collider at CERN, the world's most powerful particle accelerator. The LHC collides protons at energies of up to 13 and now 13.5 trillion electron volts, recreating conditions that last existed in the universe when it was less than a trillionth of a second old. The discovery of the Higgs boson in 2012, which was the last missing piece of the Standard Model, was the LHC's greatest triumph to date, and it resolved one of the fundamental questions about the mechanism of electroweak symmetry breaking. But the search for physics beyond the Standard Model, including supersymmetry, extra dimensions, and new sources of CP violation, has so far come up empty. No supersymmetric particles, no new heavy-gauge bosons, no signs of compositeness or new interactions at the TeV scale. This absence of new physics at the LHC has been one of the most surprising and somewhat disheartening results in particle physics in recent decades, and it has forced theorists to consider possibilities they might previously have dismissed, including the idea that the new physics responsible for baryogenesis might lie at energy scales far above what any terrestrial accelerator can reach, or alternatively that it might involve particles that are light and weakly coupled enough to have escaped detection. This latter possibility has given rise to a rich program of low-energy precision experiments designed to search for light new particles. One particularly elegant example is the search for axions and axion-like particles. The axion was originally proposed in 1977 by Roberto Pesce and Helen Quinn to solve a different puzzle in particle physics, the strong CP problem, which asks why the strong nuclear force does not appear to violate CP symmetry even though the mathematical structure of quantum chromodynamics, the theory of the strong force, contains a term that could produce CP violation. Pesce and Quinn introduced a new symmetry whose spontaneous breaking produces a new particle, the axion, which dynamically relaxes the CP violating term to zero. The axion, if it exists, would also be an excellent candidate for dark matter, the mysterious substance that makes up about 27% of the energy content of the universe and whose nature is entirely unknown. Axion-like particles appear in many extensions of the Standard Model, particularly in string theory, where the compactification of extra dimensions generically produces a plethora of light pseudoscalar fields with axion-like properties. These particles would interact very weakly with ordinary matter and photons, but their interactions would be CP violating, and they could potentially contribute to baryogenesis through mechanisms involving oscillating axion fields in the early universe, a scenario sometimes called axiogenesis, or baryogenesis from axion dynamics. Experimental searches for axions using resonant microwave cavities, haloscopes, helioscopes, and astrophysical probes have been expanding rapidly, and the next decade promises a dramatic increase in sensitivity that could either detect the QCD axion or rule out significant portions of its parameter space. Beyond the question of CP violation, there is another angle from which physicists approach the matter. Antimatter asymmetry, direct comparisons of matter and antimatter properties in laboratory experiments. The CPT theorem guarantees that matter and antimatter must have identical masses, equal and opposite charges, and identical lifetimes if CPT symmetry holds, and CPT symmetry is predicted to hold exactly in any Lorentz invariant local quantum field theory, which includes everything in the Standard Model and its known extensions. The alpha experiment at CERN has succeeded in creating and trapping antihydrogen, the antimatter counterpart of hydrogen, which consists of a positron orbiting an antiproton. Alpha has made precision spectroscopic measurements of antihydrogen, comparing its energy levels to those of ordinary hydrogen. So far, antihydrogen looks exactly like hydrogen. The frequencies of the spectral lines match to the precision of the measurements, which have reached the level of parts per trillion. The base experiment at CERN has made the most precise comparison of proton and antiproton properties ever achieved, comparing their magnetic moments to a precision of parts per billion and finding no deviation. These are beautiful and technically extraordinary experiments, and their results do not tell us why matter dominates the universe. But if a difference were ever found between matter and antimatter in these precision measurements, it would be a violation of CPT symmetry, which would overturn some of the deepest principles of quantum field theory and point toward new physics of a truly revolutionary character. Future upgrades to these experiments, including trapping antihydrogen in the gravitational field of the Earth and measuring whether it falls up or down, will push the precision of CPT tests even further. The Aegis Alpha G and G-bar experiments are currently attempting to measure the gravitational acceleration of antihydrogen, a measurement that would test the equivalence principle for antimatter. If antimatter and matter responded differently to gravity, it would be a stunning discovery, though most physicists consider it unlikely given the theoretical constraints. The possibility of matter-antimatter oscillations in neutral meson systems represents yet another avenue through which CP violation can be probed and through which the universe might have generated its baryon asymmetry. Neutral mesons, particles made of a quark and an antiquark, have the quantum mechanical property that the meson and its antimeson can oscillate into each other through the weak force, in the same way that neutrinos oscillate between different flavors. This oscillation has been observed in kaon systems, B-meson systems, D-meson systems, and more recently in B-sub-S meson systems, where the strangeness quantum number of the B-meson is non-zero. The oscillation is mediated by box diagrams in which two W bosons are exchanged between the quarks, and the oscillation frequency depends sensitively on the masses of the quarks involved, including the top quark, which makes B-meson oscillations a sensitive probe of top quark couplings. CP violation in these systems manifests as a difference in the oscillation rate between the meson and its anti-meson, or as a difference in the decay rates into particular final states. The LHCb experiment at CERN has been designed specifically to study B-quark physics with unprecedented statistical power, and it has made many of the most precise measurements of CP violation in B and D meson decays. In recent years, LHCb has seen several intriguing anomalies, deviations from standard model predictions in certain B meson decays that have generated significant theoretical excitement. Some of these anomalies, particularly in decays involving muons versus electrons, were interpreted as possible hints of lepton universality violation, which would be a sign of new physics beyond the standard model. However, more recent measurements with larger data samples have seen some of these anomalies diminish, and the situation remains fluid. The LHCb experiment will continue running through the 2030s with upgraded detectors, and its data will provide increasingly stringent tests of the standard model's predictions for CP violation in heavy quark systems. The cosmic microwave background radiation provides another window into the matter. Antimatter asymmetry problem. Not by directly measuring CP violation, but by precisely characterizing the baryon density of the universe at the time of recombination, when the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, about 380,000 years after the Big Bang. At this point, the universe became transparent to light for the first time, and the photons that were released form the cosmic microwave background that we observe today as a nearly uniform glow of microwave radiation coming from all directions. The tiny temperature fluctuations in this radiation, at the level of parts in 100,000, carry detailed information about the composition and geometry of the early universe. Measurements of these fluctuations by the COBE, WMAP, and Planck satellites have determined the baryon density of the universe to be about 5% of the total energy density, with the remainder consisting of dark matter at about 27% and dark energy at about 68%. This baryon density corresponds to a baryon to photon ratio of about 6 times 10 to the minus 10. For every photon in the universe, there are about 6 10-billionths of a baryon. This is the number that any successful theory of baryogenesis must explain. And while it sounds tiny, it represents an enormous excess. Without any asymmetry, the expected baryon to photon ratio would be exactly 0. The ratio of 6 times 10 to the minus 10 is the relic of that 1 in a billion excess that survived annihilation and went on to become all the structure in the universe. The electroweak baryogenesis scenario, which attempts to use the electroweak phase transition itself as the source of the baryon asymmetry, has been extensively studied and remains theoretically appealing despite its difficulties. In the Standard Model, the electroweak phase transition occurs at a temperature of about 100 GeV, corresponding to the universe being about 10 picoseconds old. At this transition, the Higgs field acquires a non-zero expectation value, giving mass to the W and Z bosons and to the quarks and leptons. In extensions of the Standard Model, this transition can be a strong first-order phase transition, meaning it proceeds through the nucleation of bubbles of broken electroweak symmetry within a background of symmetric phase, in analogy with the boiling of water where bubbles of vapor form within liquid. These bubble walls, as they expand and sweep through the plasma of the early universe, provide the out-of-equilibrium environment required by Sakharov's third condition. CP-violating interactions between particles in the plasma and the bubble wall can then generate a chiral asymmetry in front of the wall, which is converted into a baryon asymmetry by Sphaleron processes that are efficient outside the bubble but suppressed inside. To make this mechanism work quantitatively, the phase transition must be strongly enough first order that the baryon asymmetry generated is not washed out after the bubbles have expanded, and the CP violation must be large enough to produce the observed baryon to photon ratio. Models that can achieve both of these requirements typically involve new particles coupled to the Higgs boson, new scalar fields, or modifications of the Higgs potential. The LHC has searched for many of these new particles, and the discovery of the Higgs boson with a mass of about 125 GeV has constrained the Higgs potential quite significantly. Future collider experiments, including proposals for a future circular collider or an electron-positron Higgs factory, could measure the Higgs potential with much greater precision and determine whether the electroweak phase transition was first order or not. The gravitational wave background from a first-order electroweak phase transition would also be detectable by future space-based gravitational wave observatories like LISA, providing a completely independent probe of the baryogenesis mechanism. Gravitational waves represent one of the most exciting new windows on the early universe and on the physics of baryogenesis. When the universe undergoes a first-order phase transition, the collision of expanding bubbles and the turbulent motion of the plasma generate gravitational waves, ripples in space-time that travel freely through the universe and can potentially be detected today as a stochastic gravitational wave background. The frequency of this background depends on the temperature at which the phase transition occurred, and a phase transition at the electroweak scale would produce gravitational waves in the millihertz frequency range, exactly the target frequency band of the LISA mission, which is planned for launch in the 2030s. LISA would thus be capable of directly detecting the gravitational wave signature of a first-order electroweak phase transition if one occurred, providing the first direct observational evidence about the conditions under which the baryon asymmetry was generated. Higher energy phase transitions occurring earlier in the universe and at higher temperatures would produce gravitational waves at higher frequencies, potentially in the range accessible to the pulsar timing arrays that are already operating. Indeed, in 2023, pulsar timing array collaborations in North America, Europe, India, China, and Australia all announced evidence for a stochastic gravitational wave background in the nanohertz frequency range, a detection that was celebrated as the opening of a new observational window on the universe. The origin of this signal is still under investigation, with supermassive black hole binaries being the most widely discussed candidate. But the possibility that some contribution comes from a first-order cosmological phase transition at an energy scale above the electroweak transition remains open and exciting. The role of dark matter in baryogenesis is another connection that theorists have explored extensively. Dark matter is the name given to the unknown substance that makes up about 27% of the energy content of the universe, revealed only through its gravitational effects on galaxies, clusters, and the large-scale structure of the cosmos. Its particle physics nature is entirely unknown. It could be a new elementary particle interacting through a new force. It could be primordial black holes formed in the early universe. It could be axions or axion-like particles. Or it could be something else entirely. Many theories of dark matter also predict the existence of new CP-violating interactions, and in several scenarios the production of dark matter is directly linked to the generation of the baryon asymmetry. In asymmetric dark matter models, for example, the same CP-violating process that generates an excess of baryons over antibaryons also generates an excess of dark matter particles over their antiparticles, explaining simultaneously why the dark matter density is not wildly different from the baryon density. Models of this type make the tantalizing prediction that the dark matter particle carries a dark baryon number, analogous to the baryon number of ordinary protons and neutrons, and that the dark matter and ordinary matter asymmetries are related by the same primordial CP violation. These models have distinctive phenomenological signatures that differ from the standard WIMP scenario, including suppressed direct detection rates and possible signatures in the CMB or in cosmic ray observations. There are also more exotic possibilities that theorists have considered, including the idea that the universe might contain regions dominated by antimatter, separated from our matter-dominated region by vast distances, if matter and antimatter domains formed in the early universe and were somehow kept from annihilating completely. The observable universe might happen to be embedded in a matter-dominated domain, while antimatter domains exist beyond the horizon of our observations. This idea is appealing in its symmetry. It restores the overall balance between matter and antimatter in the universe as a whole, while explaining why our local region is matter-dominated. But it faces severe theoretical and observational difficulties. The boundaries between matter and antimatter domains would be regions of intense annihilation, producing gamma rays detectable by observatories like the Fermi Gamma Ray Space Telescope. No such boundaries have been detected, and the observational constraints severely limit the size and prevalence of antimatter domains within the observable universe. Furthermore, theoretical models of how such domains could form and survive are not convincing. The overwhelming consensus among cosmologists is that the observable universe is matter-dominated throughout, and that the matter-antimatter asymmetry reflects a fundamental asymmetry in the laws of physics rather than a statistical fluctuation in the arrangement of an overall symmetric universe. The question of whether the laws of physics are truly CPT symmetric, and whether any violation of this fundamental symmetry might play a role in the matter-antimatter asymmetry, remains an open theoretical question despite the strong experimental constraints. The Standard Model extension developed by Alan Kostelecki and collaborators provides a general framework for parameterizing possible violations of Lorentz symmetry and CPT symmetry without assuming any specific model of how such violations arise. By systematically cataloging all possible CPT-violating terms that could be added to the Standard Model Lagrangian and comparing them with experimental measurements, the Standard Model extension provides a comprehensive map of the observational constraints on CPT violation. Many of these constraints are extraordinarily tight. The equality of proton and antiproton masses and magnetic moments has been verified to better than 1 part in a billion. The equality of electron and positron masses is known to parts per trillion, and the equality of kaon and anti-kaon masses is constrained to better than 1 part in 10 to the 18th. These results confirm that CPT symmetry holds to remarkable precision in all systems where it has been tested. But the Standard Model extension also shows that there are sectors of the theory that have not yet been tested with comparable precision, and future experiments may probe these sectors. If CPT violation were discovered, it would imply that one of the foundational assumptions of quantum field theory, Lorentz invariance, breaks down at some level. perhaps at the Planck scale where quantum gravitational effects become important. Such a discovery would be one of the most revolutionary results in the history of physics. The matter-antimatter asymmetry of the universe is, in the end, a question that touches on virtually every frontier of contemporary physics. It connects the behavior of elementary particles at the smallest accessible scales to the large-scale structure and fate of the universe. It involves some of the deepest symmetries of nature and their violations. It depends on the history of the universe in its very first moments, when densities and temperatures were so extreme that the laws of physics may have behaved in ways quite different from anything we can probe in the laboratory. Solving this problem will likely require discoveries that we cannot fully anticipate today. Just as the discovery of antimatter itself and the discovery of neutrino masses were theoretical surprises that opened entirely new vistas, the experiments underway and planned for the coming decades, the precision measurements of neutrino oscillation CP violation, the searches for neutrinoless double beta decay, the measurements of the electron-electric dipole moment, the exploration of B and D meson decays at LHCb, the gravitational wave observations by LISA, the dark matter searches, the precision tests of CPT symmetry. All of these represent humanity's most sophisticated and ambitious attempts to answer the question of why we are here. There is something deeply philosophical about this endeavor. The fact that we exist to ask why we exist, that matter survived to form stars and planets and brains capable of pondering the conditions of their own creation, is itself a consequence of the asymmetry we seek to understand. We are the children of that 1 in a billion surplus. Those extra particles of matter that were not annihilated because of some subtlety in the interactions of the very early universe, that we have not yet fully deciphered. Every atom in every human body is a survivor of the great annihilation, a relic of a microscopic imbalance that played out in time scales of billionths of a second after the birth of space-time itself. The universe we inhabit, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, with its planets and moons and nebulae and black holes, with all its beauty and complexity and the life that has arisen within it. All of this is nothing but the thin residue of an asymmetry so small that it staggers the imagination, and yet without it nothing would exist. The universe would be pure light, pure radiation, a featureless and lifeless sea of photons in a space with no structure, expanding forever in perfect sterile emptiness. The mystery of matter over antimatter is therefore not merely a technical question in particle physics or cosmology. It is a question about the very possibility of existence, about why the universe is the kind of place where something can exist, rather than nothing, where structure can form rather than dissolve, where life can arise rather than being forever prevented by the merciless symmetry of a world without bias or preference. The answer, when it finally comes, will tell us not just about the properties of quarks and leptons and bosons, but about the deepest nature of the laws that govern reality, about whether those laws contain within them a preference for existence over non-existence, a bias toward the complex and the structured over the empty and the symmetric. It may turn out that existence itself is the product of a broken symmetry, a deviation from a perfect balance that could not be maintained, and that the cosmos we inhabit is, in the most literal sense, a consequence of imperfection. In science, as in so many other domains of human experience, it is the imperfections that make everything possible, and the most important imperfection of all, the one that made the universe and everything in it possible, is the tiny, mysterious, not yet fully understood preference that nature showed in the first instance of time for matter over antimatter.